Good evening, Internet. I am Matt Buyak, and in this video, I'll show you how to calculate the sum of divisors of a natural number given its prime factorization. So this is the third video that I've done on the prime factorization of numbers and working with the prime factorization of a number in C and C++. So if you haven't seen the first two videos, you might want to go back and give those a look. However, they're not strictly prerequisites for this video. Those videos were mostly about how to calculate the prime factorization, and I showed two algorithms for doing that. This video is going to be showing two important results that we can calculate from the prime factorization once we have it. Now, if you go back to the problem archive here, it was this problem number 21, that sort of inspired me to make these three videos on prime factorization. You can see it asks a question about amicable numbers, which are defined in terms of the sum of their divisors. And then you see down here, problem 23, which we have yet to solve, also asks a question involving the sum of the divisors of a number. And so this is a very common theme in Project Euler problems. And it's certainly a tool that we would like to have in our toolbox. And so that's going to be the focus of this video. Now, it turns out that there's actually a very nice expression for the sum of the divisors of a number given its prime factorization. But if I were to just show that to you, it's not at all obvious why it's correct. And so most of this video is going to be looking at some analysis, showing some examples, trying to get some intuition as to why our final result is actually true. And so let's get into it. I'm just going to create a new file under our notes directory. We'll call it factors.txt. OK, and so if you didn't watch the first two videos, you might need a refresher as to what exactly the prime factorization of a number is. And it basically just means that we're able to write any number, positive integer that is, as the product of prime powers. So you might have some prime p0 raised to the power k0 times p1 raised to the power k1 times some prime p2 raised to the power k2, and so on and so on. And there's a theorem, the fundamental theorem of arithmetic, which says that any natural number can be written in this way. OK, so let's take as an example the number 360. We'll say suppose n equals 360. And we want to consider the sum of the divisors of the number 360. So let's just note real quick that this number is going to be equal to 2 cubed times 3 squared times 5. And so that's the prime factorization of 360 here. You'll note that I'm saying the prime factorization. It's this representation is unique. That's also guaranteed by the fundamental theorem of arithmetic. OK, so now I'm just going to write out the factors of, the divisors of 360. This might seem a little bit tedious, but it shouldn't take too long. So we'll have, let's see here, 1, 5, 3, 15, 9, 45, 2, 10, 6, 30, 18, 90, 4, 20, 12, 60, 36, 180, 8, 40, 24, 120, 72, and 360. Okay. And we want to consider the sum of all of these numbers. I'm not going to make you suffer through watching me add them up on the calculator. I don't think that's really necessary. But there's a particular reason why I went through the trouble of listing all these factors out like this. And I want you to notice that we can group these factors into 4 different groups. So at the top here, we'll have the odd numbers. So that's these 6 numbers here. And then we'll have the numbers that are divisible by 2, but not divisible by 4. That's the next 6 divisors. You'll see that I've ordered these in a particular way. You may have wondered when I was listing them out, why I was listing them out in the order that I was. And there was a very specific reason for that. So then you, in the last group, have those divisors which are divisible by 8. Yeah, and so you can see that this nicely splits the divisors into 4 groups like so. And now we can factor a power of 2 out of each of these groups. So if we're considering the sum of these numbers, let's write it as a sum. So we'll just do this. Okay, and then we'll have plus. Again, just a little bit of tedium here. Shouldn't take too long. Okay. And as I mentioned, now we're going to factor a 2, a power of 2 that is, out of each of these sums, or each of these terms. Oh, I made a mistake here. This should be 15. Okay, and then we can factor a 4 out of this. And we can factor an 8 out of this. And now it may be becoming clear why I ordered these divisors the way that I did. You'll see that we now have the same sum for all 4 groups. And so we can factor this whole thing as equal to 1 plus 2 plus 4 plus 8 times 1 plus 5 plus 3 plus 15 plus 9 plus 45. Okay, but now we can repeat the process. Here we extracted all of our powers of 2. We can now do the same thing with powers of 3. So here we have 1 plus 5. We can factor out here 1 plus 5. And then here we can factor out a 9 times 1 plus 5. And so this is going to become 1 plus 3 plus 9 times 1 plus 5. And so this is essentially our main result, is that the sum of the divisors of a number can be factored like this. Now, this isn't a proof or a proper derivation, but I think this will give you an idea of how we get this result. And I'm actually not going to show this derivation in the general case. It mostly looks exactly like what we just did. Okay, so let's get a little bit formal now and write an expression for this. So let's let d of n be the set of divisors of n. Let sum of d of n be the sum of the divisors of n. Just a little notation there. And now we can say that sum, I made a small typo here. The sum of the divisors of n is going to be given by the product, I going from 0 to, call it p minus 1. We'll say that a capital P is the number of distinct prime divisors of n. And so then that's going to be the product over the sum, and the sum is going to go from j from 0 to what is it, k ki? Yes, of what is that? Pi to the j. Okay, so that's the formal representation of what we've done here. But you may recognize this section here. This is just a geometric series, which we've looked at in, I think it was all the way back in the analysis for problem number 2. That was the third video that I made on Project Euler problems. I believe I included in that video a derivation for the expression for the geometric series. And I'll just repeat that here without proof. And so that's going to be if we have an expression such as this. Then we'll just say, from problem number 2. The sum is just going to be equal to what is it, pi to the ki plus 1 minus 1, that whole thing divided by pi minus 1. Okay, so as an example, we'll say for example, if we have 1 plus 2 plus 4 plus 8 would be equal to, that's 2 to the 0 plus 2 to the first plus 2 squared plus 2 cubed. And then by our expression up here, that's just going to be equal to 2 to the 3 plus 1 minus 1 divided by 2 minus 1. And that's going to be equal to, should be 15 there. And you can check that easily enough. Okay, so this means that we can combine these now to get our final result. Okay, say here key result. Okay. Now, before I start writing some code for this, there's a few other things that I would like to note. One is going back up to this expression up here. I forgot to mention, this actually gives us a nice expression for the number of divisors of a number. And so you'll notice that if we were to expand this out, you multiply this expression out, we get the sum of all the divisors, as we just showed. And so the number of terms in that expression is going to be our number of divisors. And so that number is just going to be equal to the number of terms in this sum here, multiplied by the number of terms in this sum here, multiplied by the number of terms in this sum here. So let me just add in here note. Actually, let's put this after our definition here, because then we can say note that the size of d of n, remember d of n is the set of our divisors, is going to be equal to, so this is just the number of prime powers, or powers of the prime p0 which divide n, multiplied by the number of powers of the prime p1 that divide n, multiplied by the number of powers of p2 that divide n, etc., etc. And so that's just going to be the, let's see, product. I is going again from 0 to p minus 1. And so then that's just going to be ki plus 1. And so therefore n equals 360 has, what is that, 24 divisors. And that's going to be, just to spell that out more explicitly, that's going to be 3 plus 1 times 2 plus 1 times 1 plus 1. Okay, so that's our other key result. Okay, so now we want to add these to our prime factorization class. Yeah, so let's open that up. That's going to be under common factors.h. Okay, so let's just add a few new methods here. We'll call this let's see, number. We'll say count divisors, and sum divisors. Okay. And we'll open up our source file. And let's see, we'll put that right down here. Excuse me, factorization. Okay, so let's start with count divisors. That's the easier of the two. So we'll say count equals 0 equals 1. We're going to be multiplying, so let's do it that way. And we'll need I. So we'll say for I is 0, I is less than. It's just going to be factors.size. and we'll say count multiply by, let's see, factors I dot exp plus 1. Return count. Okay. Oh, I made a minor typo here. All right, and then similarly here we'll say sum is equal to 1. Again, we're going to be multiplying, and so we want to start off with a ironically a sum of 1 rather than a sum of 0. And then we'll need I and j. Let's do this also. So there's not actually a function in the standard template library for exponentiation of an integer. There is a method for, or a set of methods, in fact, for floating point values, but those are less efficient, and so I'm just going to basically reinvent the wheel here. Okay, so going back to our notes. Okay, so we're going to take the product over over all the prime divisors of our number, and for each one we need to calculate that prime raised to the k plus first power. Okay, so let's say for I equals 0, I is less than factors dot size plus I. And we'll say actually let's not initialize this here. We'll say pow is equal to factors I dot prime. And then for j equals 0, j is less than factors I dot exp plus j. And this is a little bit hackish. Let's do it this way. Let's initialize it to 1, and then go to, I guess 6 of one, half dozen of the other. But in any case, yeah, that should work. Okay, so then we're going to say pow times equals factors I dot prime. So this should get us pow is equal to r prime raised to exponent plus 1. Okay, so then we're going to say sum times equals, and then this is going to be pow minus 1 divided by factors I dot dot prime minus 1. Okay, and I think that should be correct. And now let's, as a quick test, we open up our factors test. Let's just add here printf sum of divisors of 360 equals, and then we'll say, oh, excuse me, we need to do f dot factor 360. And then we'll say f dot, what do I call it, sum divisors. And then, actually, let's put this first. Count of divisors of 360 equals f dot count divisors. Okay, it looks like no compiler errors. That's always nice to see. And okay, and I didn't actually calculate the sum of the divisors of 360, so let's go back to our notes really quick and just make sure that that I've done that correctly. Oops. Okay, so we have, what is this, 15 times 13 times 6. Yes, and so that gives us our expected result here. Okay, so it looks like our code is working as intended. That's always nice to see. So now let's add a little bit more comprehensive testing here. Okay, so for our existing tests, we're iterating over the numbers 1 to 10,000 and exercising our prime factorization class for those numbers. And so we'll want to do something similar here. And the way we're going to do that is just by brute forcing these values that we've just calculated. And so if we say, let's see, uint32t, we'll say count divisor. Actually, let's we'll call it divisor stats, because we can actually just write one function that does both. And so we'll say uint32t n. We'll say uint32t reference is going to be sum, and uint32t reference count. And this is because we're just going to try all of the divisors, up to n, and calculate these values. And so there's no real reason to separate this into two different functions. We're going to say, for div equals 1, div is less than or equal to n plus div. We'll say sum equals 0, count equals 0. And then we'll say if n mod div equals 0, then we want to say plus count, and sum plus equals div. Okay. And so let's add here sum and count. So we've already calculated the prime factorization for our number, and so we should just be able to say here, what did I call it, divisor stats? Yes, divisor stats. Okay, we can say divisor stats, and that's going to be I, and sum and count. Let me make sure I got the order correct there. Sum first, count second. Yes, that's correct. Okay, so this should brute force our metrics for us. And so now let's just make sure. We'll say if f dot let's see. Yes, sum divisor f dot sum divisors is oh, let's actually let's do this. We'll say sum expected, count expected, sum actual, count actual. Okay, so then we can say, let's see, this is sum expected, count expected, sum actual equals f dot sum divisors, and count actual equals f dot count divisors. So then we can say if sum actual not equal to count actual, printf let's see, sum of divisors of %u is %u expected %u. And so that's going to be I sum actual and sum expected. And then we'll say go to end. And we'll just do something similar for the count of divisors. Okay, so then we'll say if count actual. Oh, I've done something rather silly here. This should be sum expected. Okay, and I got it right the the other places. Okay, all right. So now we have if count actual is not equal to count expected, then we say number of divisors of %u is %u expected %u. So that's going to be count. Okay, and then we can get rid of this section here. It looks like I've made a mistake. Does not like my function divisor stats. All right, so we're taking uint32 and two uint32 references, divisor stats. Oh, I see. I have an extra S there. Okay. And we'll say factors test. Success. Okay, great. So we've added new code for calculating the sum of divisors of a number and the number of divisors of a number, and we've wrote some tests to verify that is correct to the best of our knowledge. So armed with our new tools, in the next video we'll move on to solve problem number 23.